Okay, good afternoon, everyone. Thank you for joining our first industrial transition series by IETS. Okay, everyone keeps on joining the webinar, but we'll start very soon as we have a busy schedule. Okay, so the numbers are still rising, but I believe that we should kick it off. So, good afternoon, everyone. Thank you for joining the first industrial transition series dedicated to electrification in industries. So I will moderate the webinar. And here you can see the whole agenda. Ellen Johansson from IETS will make an introduction to the TCP IETS. And then followed by Jonathan Mancada, that is the task manager of the task electrification in industry. So that will be two short introductions of around 5 minutes. And then we'll have three major projects from different TRL. So the first project will be hybrid fryer presented by Professor Christos Anezeris, then followed up by the project Electra by Bodil Williamson, and finally Andrew Reynolds will share the new fifth area projects of the 100% electric glass furnace. And I will leave the floor on the mic to Ellen Johansson from IETS. And you can take control of the presentation.
Yeah. Right. Thank you, Leo, and hello, everyone. It's nice to see so many of you. I'm Helene from the IETS Secretariat, and with me today is also my colleague, Per-Åke Frank. And what you can see here on the first slide are the flags representing our member countries. The last one, the UK, actually signed yesterday. And you can also see the full name of the TCP, and then you understand why we use the acronym. And then I have to change there. The IETS TCP is part of the IEA Technology Collaboration Program, which is a global network for international collaboration. There are about 40 TCPs focusing on, for example, heat pumps, energy storage, buildings, transports, etc. And the IETS TCP focuses on energy use in a broad range of industry sectors. The work program ranges from aspects relating to development of processes and energy technologies to overall system analysis and energy efficiency in industry sectors. The general aim is to strengthen international cooperation on energy savings and GHG mitigation in industry. And our work is organized in so-called tasks. And here you can see a list of running tasks. I will not go through them, but you can find all information about them at our website. And Jonathan will also introduce you to task 19, electrification in industry, in a bit. As you can see, some of the tasks are technology oriented and some are system oriented. So, why participate in the IETS work? What you get the chance to take part in an international collaboration consisting of so far 16 countries for networking, achieving various synergy effects and knowledge transfer. You also get access to various reports that are not open to everyone, as well as workshops, webinars, publications, etc. And if you want to participate in a task, you bring your already funded projects for sharing experiences and results. In this TCP, there are no means for funding projects. We have no calls, and you are expected to take active part in various activities like workshops and report writing. And if you want to join a task, contact the task manager to discuss participation, or talk to your country delegate or us at the Secretariat to express interest. To join a task, you have to belong to a member country or become a sponsor. But we also welcome new countries as full members, of course. And at our website, you can find more information about the task work, events, available publications, contact details, etc. A good way to keep track of what is happening is to subscribe to our newsletter, and then you'll also get the invitation to this webinar series. You can also follow us on LinkedIn, and we have a LinkedIn group where we can discuss things. So feel free to join. And thank you for listening, and please contact us. All contact details are at the website if you want to know more and take part in this collaboration.
Thank you very much, Eileen, for the presentation. I will invite Jonathan to follow up. You can take the control, and just also completing my introduction. So as I've said in the chat, don't hesitate for any presentation to ask your questions in the Q&A section, and I'll address them for smoothen the webinar. We've not allowed the cameras on microphone. I'm sorry for that, but you can always react also with the reactions, I believe. So don't hesitate, or in the chat directly. And Jonathan, up to you. Thank you.
Thank you, Leo, for the introduction. So good afternoon, everyone. I am Jonathan Moncada from TNO in the Netherlands. I am the task manager of this electrification task 19 on electrification of industry, and I will tell you a little bit in just 5 minutes what the task is about. So why to electrify industry? Yeah, we need to decarbonize in the fossilized industrial sector, and that is an interesting question in an ideal world, and making an analogy with the ideal equation of a state. Everything will be easy, a piece of cake, especially when green electricity is available, when the electricity is cheap, and when industry is hardly affected by any change. But I would like to stress that that is actually not the case, and we have this little guy here starting to think. I starting to think on questions like, well, but electricity is intermittent, right? There is not possibly not enough capacity installed for green electricity in the different countries, and also to dedicate to industry is also a challenge because there could be competition with electricity and resources. Oh, is it the focus only on direct electrification, but what happens with indirect electrification, like electrification for hydrogen, for instance, as feedstock for industry? How do we deal with the intermittency of renewable energy? Buffering capacity, is hydrogen storage needed? Is batteries needed? But how expensive will the system be? In some cases, the technologies are still at very low tiers. Will society accept those changes? Like if we direct a lot of energy to industry, industry is not flexible per se. Do we need to redesign industry? And what could be the potential impacts of that? So all of these questions make this little guy to be a little bit dizzy, and then it comes a bunch of dilemmas that needs to be addressed and tackled. So to move ahead into learning from what the different countries are doing in the area of electrification of industry, this task started in 2019. I've been involved since the beginning of the task. We have been involved in 3 subtasks for now. The first subtask was really on mapping the scene, really looking what was happening in the topic of electrification and getting a critical mass. And last year we finalized subtask number 2, and it was a successful subtask on looking at different aspects at the system level of industrial electrification, included both direct and indirect. And this year we have started with a new subtask in which we are in the phase of getting the critical mass to participate in our subtask. And the objective is basically to strengthen what Helene just mentioned in the previous presentation, is to really strengthen the international ecosystem and to get some knowledge exchange and lessons learned from the different countries on different areas. So to speak a little bit about the participating countries in this specific subtask, we have confirmed participation from organizations from Italy, Sweden, Austria, Canada, Denmark, Germany, France, the Netherlands, Finland. Colombia is really keen to become a sponsor. Switzerland, and I just received an email a couple of minutes ago before joining that Sintef from Norway is also participating. And now that the UK has become a member, I think it's very much likely that we will also tackle and chase some UK organizations. But for now, it's quite a large consortium that has been built around, and we expect to start at our first meeting in September for this specific subtask. And the thematic areas that we will cover in our subtask number 3, it comes from what's happening in different countries, like current status of industrial electrification installations. So we can have a bit of a survey in the different countries, what is happening in reality, analysis of case studies on technology development and implementation. There are groups really working, like for instance, in heat pump technology development. But also we go a little bit beyond than that, and we analyze also case studies on systems analysis and impacts, like those that deal with techno-economics, life cycle assessments, or even energy system modeling. And a bit of expert opinions on the role of process integration and energy intermittency, like what to do with those challenges. Will industry needs to be transformed, and how. And last but not least, a very interesting topic that will be covered in this subtask is how electrification stands against other defossilization measures, like for instance, the use of biomass, circularity options, and energy efficiency improvements, and whether a merit order for electrification can be developed. That is from my side. It's very short, but I hope to have enlightened you a little bit on what we are doing. You still have time to join us. So if you have any question or would like to join us for this upcoming task that will kickstart in September this year, please contact me. Thank you.
Thank you, Jonathan, for the indeed short introduction, but we don't hesitate to reach out to Jonathan, and I will invite Christos Anaziris for a longer presentation of the project Hybrid Fire. You can take the control.
Thank you very much, Leo, and thank you very much also all of you for having the opportunity to present a little bit some issues of hybrid fire for metallurgical and ceramic applications. And somebody would say, what is hybrid fire? It's a project with partners coming from the ceramics and refractories like Refratechnik, company like Frekion Mala dealing with microwave technologies, as well as Pleisner-Gus, a company from the steel plants. And somebody would say the project, when has it started? It started 2 years ago, and we have still 2 years more. And the project explores different combinations of heating technologies. And on the one way, by using conventional gas burners and or electrical heating elements and or microwave plasma burners. So we want to see what is the impact of the combination. On the one way, in ceramic processing, solid phase, and ceramic processing, we would like to see what happens in the sintering. And for the guys who are not familiar with the sintering in ceramics, it's a kind of a heating treatment process where a powder already shaped into a desired form is transformed into a more dense solid material by bonding the particles. Mainly you have a big one particle and a small one, and the small one disappears via diffusion and is incorporated in the matrix of the big one. So we have a grain growth and a shrinkage, and fine particles present a higher shrinkage, get more densified structures, and on the other way, coarse grain materials like refractories, like Refratechnik products, we have less shrinkage, but we have other plus properties at elevated temperatures. And of course, not only the solid phase, we would like also to see what happens in metallurgical processing like melting steel. The trip has already started, as also the speakers before have mentioned, and pay attention, there is no labyrinth. Yes, a lot of ways and paths will lead to Ithaca, but at the end of the day, I believe this will be a kind of a combined process. Just a moment. We have dealt in the past in basic research, but we're still keeping going with supporting by the German Research Foundation in means of light design, metal and ceramic or refractory recycling, but especially also with electrodes, coarse grain materials for high temperature electrodes, metal ceramics, composite materials and structures. But today I would like to concentrate in the hybrid fire. And the next slide is coming from the metallurgy as we have it here in Freiberg. We see on the left a crucible which has steel which already melted and a very slight spot in the middle. This is a kind of nozzle, and this nozzle is based on alumina oxide. Why alumina? I will immediately speak about it. On the one way, aluminum oxide is a material which is a low-cost material. On the other way, it presents excellent corrosion resistance against acid as well as basic environments. And one problem of it is the thermal shock resistance. So we have to improve it, for instance, by making layer by layer design as it can be made by 3D in order to be able to withstand thermal stresses, thermal gradients. Of course, somebody would say, yes, I'm familiar and I'm coming from flame spraying technologies or plasma technologies. Then you have also a layer by layer. We are doing also this kind of approaches. You do not need a kind of a sintering of your component. You can immediately use it. But once again, we are interested in the sintering processes. And somebody would say, why alumina are you so interested for this kind of material? Because it's the only material in the ceramic area which can be used in hydrogen and in water steam atmospheres. So it's a material who, if we can improve the thermal shock performance, it can be used as a burner component for this hydrogen technology. Somebody would say alumina, yes. What happens if we have a little bit silica? Because aluminum silicates is an approach to have improved thermal shock. We see the blue square or the orange or yellow triangles. These are alumina silicate ceramics or insulating materials, and we see that we have a great negative impact. So we have a high relative mass loss at temperatures above 1400 degrees, much higher in comparison to the classical pure alumina, the red one, the red circle, which is a pure alumina system. But this is not only the case in the silicate area, this is also in the case in magnesia. And magnesia bricks are the lining materials for rotary kilns. And we see in the middle such kind of bricks. And we have done a following experiments. We have made a pre-treatment of such kind of bricks, magnesia bricks, in pure natural gas, or in pure hydrogen gas, or in 50-50. So 50% natural gas and 50% hydrogen. And we have seen that, for instance, if we have a pre-treatment at 200 degrees Celsius in means of the hydrogen atmosphere, we have a positive impact if we follow with the 1600 degrees sintering in a natural gas, so in a conventional furnace. We have an increase in the tensile strength, but at temperatures above 600 degrees Celsius, we have more than 1/3 loss of the strength if we have a kind of hydrogen atmosphere. And this is detrimental if we keep in mind that such kind of bricks have to live more than 1 year in the rotary kiln. Somebody would say, do you see this only in case, do you see this kind of only in case of strength? No. You can see within a kind of calorimetry, you can identify different kind of reactions. On the left, the blue curve is a pre-treatment at 200, on the right at 600. And the black curve is the kind that we have normally in natural gas. So we see, in spite of the fact that we speak about hydrogen, at different temperatures, different kind of reactions will appear. somebody would say, why are you focusing on sintering? Because the sintering is the most energy intensive step, with approximately more than 70% of the consumption of energy. And this is not only in means of refractories, but as always for the roof tiles, technical ceramics, functional ceramics. And we want, in our case, to electrify the high temperature area of sintering by using mainly the microwave plasma burner. Somebody would say, do you have a little bit experience with microwaves? Yes, we had in the past, or we have a kind of a microwave coupling device for drying or also for binding or debonding processing with magnetrons at 5.8 gigahertz and 2.45 gigahertz frequency. But we have also a small laboratory device where we have done preliminary tests with 6 kilowatts microwave burner, as well as a bigger hybrid sintering device equipment with 1 cubic meter chamber, where we have all the three technologies. That means microwave plasma burner, natural gas, hydrogen, but as well as normal electrical heating elements, as we had normally, where normally functional ceramics or advanced ceramics are sintered. In the past, we have used the direct microwave coupling, for instance, for making silicon nitride, reaction bond silicon nitride, or to couple the soot in a diesel soot filter to burn it out to regenerate a diesel soot filter. Or we have seen also the positive impact. If you have already a melt, like an aluminum melt, you have an interaction with microwaves and you can keep the temperature, and so the melt can be transported on the motorway from the melter to the end user. Yes, we want to use microwave plasma burners because we can directly use the electrical energy. We do not have a consume of cathode material, and the most important is we do not have a microwave coupling. It's only the air is getting hot, like in the conventional gas burners. Somebody would say, have you already done experiments with 100 kilowatt? Yes, it's working. And the most important is we will have 1 cubic meter chamber, so we have the same volume, and we can see the electrical efficiency on the one way, and on the other way, the quality efficiency, because the atmosphere has other radicals which can interfere and change also the quality of our products. Where do we want to go in terms of the projects? The positive results have to be transformed to a continuous furnace, something like 100 meters now, where normal refractory or silicate ceramic products are sintered. Of course, we have to keep in mind, it's not only the ceramic product which has interactions with the atmosphere of the different kind of heating processing routes, but also the thermal insulation as well as the refractory lining. And we do not want to use the H2 burners. We have seen already interactions in the insulating materials or in the magnesia. We want to successfully substitute some, and at the end of the day, if it's possible, all the CH4 burner systems. That means we are dealing not only with processing of materials, but also we develop materials for the new processing route. Some results with the laboratory, small one, device, we have seen that in case of magnesia, fine magnesia, independent if you have electrical heating elements or the mixed with microwaves, we have the same level of strengths. We have seen in case of zirconia, which is an advanced ceramics with high fracture toughness, but as well as a material which is very interesting due to its ionic conductivity or electrical conductivity above 1000 degrees Celsius. Normally, it's sintered discontinuously in a chamber kiln where molybdenum disilicide heating elements are used. And we have seen and we have compared normal conventional heating using heating elements as well as the microwave plasma. And we have seen that we have decreased 50% approximately the heating up time. And this would be perhaps very interesting if we leave and go away from the today discontinuous approach to a continuous one. So electrification with the aid of microwave plasma burners, we have fluid dynamics mainly like the conventional burner. So this kind of technology would open also the approach for advanced ceramic, construction ceramics, as well as functional ceramics. And somebody would say, do you have also used it in means of silicate ceramics, this microwave plasma? Yes, and we have compared it. I have triggered the scanning electron microscopy pictures, microstructures, and perhaps you can identify in your screen on the left, downstairs, on the right, downstairs, you can see some like needle-like structures, which increase the fracture toughness on the one way as well as the strength. And the question would be as a result also additionally a light design. And if you would use plasma, you change also the surface properties of your system. We have seen this by using alumina-rich bricks as a lining in a ladle, and we have gone in a heating microscope. On the one way, by using a microwave plasma burner treated surface on the left below at 1580, and on the right by using normal electrical heating elements in an air atmosphere. And we have seen that the wetting behavior is completely changed. That means we have less wetting, that means higher wetting angles, that means less infiltrations, and at the end of the day, also higher corrosion resistance. And somebody would say, yes, can this technology, that means the high temperature electrification, also applied in conventional traditional vessels in the metallurgy, like in a Tandis vessel? Normally, this kind of a vessel where 80 or up to 90 tons of steel as a buffer device are applied in a continuous steel casting. They are preheated with natural gas burners, so you have the CH chemistry which interacts with steel, not in positive means. So what would be if we have integrated core cell electrodes and use additionally also microwave plasma burners? Less thermal shock, less corrosion, and at the end of the day, a higher durability of the whole system. Somebody would say, if you use microwaves, and we have spoken also about microwave coupling, would be also such kind of combination. That means you have one generator. On the one way, you use the microwave plasma burners to melt a metal like aluminum or steel. And then, as we have shown before, now you can have an interaction by microwave coupling because we don't have a kind of reflection. We have a microwave interaction. So what would be the impact? Or use this in rotary kilns. Of course, we can use induction plasma burners. Today, we will hear also about such kind of approaches. And at the end of the day, you can also use direct electrical coupling with microwave plasma burners. That's it for today. We can discuss some issues. I would like to thank the industrial partners which are giving the path, the way, and of course, it's an industrial-oriented examination, exploring, investigation of such kind of technology, and of course also the Ministry or the Federal Ministry for Economics and Economic Affairs and Energy, the BMWA, as we say today in Germany. Thank you very much for your attention.
Thank you very much, Christos, for the presentation. Before going to the next presentation, we'll take the first question in the Q&A. So that's a double question, actually. Could you please tell why the air is selected as a carrier gas in plasma? And what is the difference if we use CO2, since using CO2 can already give higher concentration flue gas in the kiln, making the capture easier?
Absolutely. We want to substitute the today CH4 burners. That's why we want to keep air. And pay attention, yes, CO2 is also interacting with some of our ceramics, like zirconia. They are destabilized. Also the magnesia. So we create failures in the structure, would have a detrimental impact at the end of the day during the application, yes.
Thank you for
using air and no CO2 if it's possible. Of course, you have other impacts with plasma and CO2 atmospheres, or if you add catalytic additives.
And in the question, it was also precise about cement kiln. I've understood the presentation was really focused on ceramics and metallurgic applications.
Absolutely.
Yeah. So it's not the cement case. Cement case is the next presentation.
Absolutely. But it was only the giving the hand to the next presentation. And of course, we would like also to see this because the one way it's cement, clinker and whatever. On the other way, you have also other inorganic raw materials that you can pre-treat with plasma.
Thank you for clarification. And I may have just one last question.
Yes, please.
Regarding, do you also monitor, or will it be monitored, about the potential savings in energy with
Yes.
hybridization? Yeah.
Yes. The good thing is we have the same chamber, the same volume. That means we can have individually the technologies, but as well as combine them. And so we will see the impact of electric, absolutely, because we are monitoring this. So we will see what happens with 100, which temperature do you need? Because we have seen with the radicals that are created in means of plasma, you can decrease perhaps a little bit the temperature, the sintering temperature. You can be faster. And at the end of the day, it could be that the combination of two technologies will lead to the goal or fulfill the task. One critical issue that has to be always kept in mind, we have plasma. What will happen with the NOx? How you control them. So this is an issue. I've not spoken about it. But you have seen we have changing the silicate structure in needle like. This is due to the interaction of the NOx or whatever is in the atmosphere with the silicates, for instance. So this has to be really explored product by product.
Okay. Thank you for the clarification, Christos. There are no further questions in the Q&A. Don't hesitate, and maybe Christos can answer directly in the chat if you have a follow-up question. So thank you, Christos, and we will continue. Yes, thank you. With Bodil Williamson, I will let you take the control and present Project Electra.
Yes, thank you very much for that, Leo. And now I will talk about clinker related to the questions given. Okay. Sorry, I need to make my like that. Yeah, so my speak will be about high temperature heating of cement with plasma technology, or as I have renamed it here, utilizing thermoplasma for the production of cement clinker. I'm Bodil Williamson, and I work today at Heidelberg Materials and also at Umeå University as an associate professor in Sweden. And the electrification research and development we have been doing is partly funded by the Swedish Energy Agency and also by European Union. And that is what I will present. Thanks for giving me the opportunity. So, is electrification in cement production a new idea? Or are we reinventing the wheel? Because there are 2 patents filed in Sweden already in 1912 and 1919. But yeah, so one can always ask ourselves if there is something new, but of course it is. And I will tell you about that. And I will start with talking a little about cement clinker, our product. It's unique in one way. Here you see a microscopic picture. You can see the scales here. This is the middle product clinker, which we then grind with gypsum and then get this gray powder, which we mix with water and we get a hardened concrete product. And what I would like to highlight here and what is unique with producing clinker is that we need a lot of sea as here you can see in the picture, C3S are all these brown sharp-edged clinker minerals. We need to have C2S, and we need to have C3A and C4AF. And C is here in CaO, quite a different way in chemistry for cement clinker chemistry. And where do we get all the Ca? Yeah, we get it from calcium carbonate. About 80% of the raw material we have in cement production is from calcium carbonate. And to achieve this structure, we need to have the material as in a high temperature as approximately 1500 degrees. So what happens? Well, we need fuel to heat the material, and when we heat it, we get CO2 from the raw material. So that means we have double the problem or the challenge of abating CO2. Here is the chemical reaction of what happens with calcium carbonate when heated. We need energy and we get CO2. This is for us to get free CaO. And if we put some figures on it, we see that 1/3 of the CO2 emissions come from the energy, only 1/3. So the major part of the CO2 we get when in cement production is from the raw material. So we have some, as I said, twice the challenge. And approximately 8% of the global CO2 emitted from industry is from the cement industry. So that is a challenge we need to face. If we look at a typical scheme of what happens when producing 1 ton of clinker, we need limestone, we need fuel. Many plants use biofuel and other fuels, of course, and then we calcine it and we put it in a rotary kiln. Totally in the flue gases, we have 0.67 tons of CO2. And we need energy of 3.3 gigajoule. And how to handle this? It's not enough to remove the fuels, because then we still have a lot of CO2. 2/3 of the CO2 is still there, as I showed. So what do? Yes, of course, we should use the most technically mature technology, and that is amine capture, post-combustion and together with amine, and that is a liquid process. I will show some picture later on. So to be sustainable, we need to capture all the CO2 in our flue gases. We need to clean them, and we need to compress them and then put them away for geological storage. And this will then give that we need the same amount CO2 as in the previous picture. We need to collect that, and with this scheme we do that, but it costs a bit more energy. From 3.3 gigajoule, we now need 5.5 gigajoule to make this happen. But then no CO2 is emitted to the air, which is of course the aim with the whole thing. And that is something we do. And the best thing with this is that since it is a post-combustion technique, the quality of the product is unaffected. So it's still the same good quality of the product, even though all the CO2 is removed from the product. But the energy consumption is high. And I want to show that already today, this is a very recent ad from 12th of May last week, that is. The first in the world full-scale industrial post-amine combustion started. So the first 1,000 metric tons CO2 was captured at the Brevik plant in Norway within Heidelberg, which we are very proud of. And this is of course good, but is there something we should do even better? Is there something we can do even better in the future to decrease this energy consumption. As I was talking about, it increased, but here in Brevik, they capture 50% of all the CO2 in the flue gas, and that is due to the waste heat from the plant is then able to be used. So the energy for this captured CO2 is not as high as 5.5. That is a theoretical value when you don't have any waste energy. So this is better. But for the future, if you don't have waste from your plant, is there something you can do else? Of course, then we have to test can we electrify the cement production? And to give you the advantage of electrifying the cement clinker production, I'd like to show you this picture. If you remember the two last ones, if we then electrify the production, so all the heating is done with some electrical source. It means that only the CO2 from the raw material need to be collected. So from 0.67, we can decrease it to 0.42 ton per ton clinker produced, which is 37% decrease. And the energy can be decreased to 4.8 gigajoule, which is to be compared with the 5.5 for the post-combustion amine technology. And as you also see, there is quite a lot of other parts from the process that is not needed. So the two benefits that would give us from electrifying the production is that we don't get any CO2 from the fuel, but the biggest advantage is that the CO2 in the flue gases is already very concentrated because we use some heating that will not change, that will only give what we get from heating the raw material, and that is the CO2. And I will come a bit further with discuss that further soon. This is what I've already said. We will achieve this with electrification. We will reduce the fuel carbon dioxide. We don't need to do any fuel handling. The exhaust gases are already ready to be captured. And it is a very competitive decarbonization cost since the capex and opex for the flue gas cleaning is much, much lower since the CO2 in the flue gases is very highly concentrated already when it comes out from the kiln. So the challenges here is that the production process is totally different. It happens in another atmosphere. So that is something we need to find out what will happen. And other positive effects, possibilities with electrification is that our production can be divided in two parts, so to say. We have the calcination step, and then we have the even higher process in the rotary kiln. And most of the CO2 is coming from this part of the process, and also the most of the energy comes from this process. So if we just electrify the one part to the left, then we will achieve close to 80% of all the CO2 being separated. And then if we'd like to also electrify the rotary kiln, then we get 100% electrification, which could be a very nice step in the development of the electrification of the cement process. And of course, we have to have the renewable electricity available. So, but if we then try to find a good way to heat the material, I should show this first. Of course, a 1 million ton clinker production would theoretically need 175 megawatts, so that's quite a lot. And we need to be able to make this work, have to have an efficient electricity to heat concept. We need to have an efficient heat transfer mechanism. I will show you some slide on this soon. We need to have good reactor concepts, and we need to upscale the effect of the electrical heaters. Those today available are quite small, and the lifetime of the electrical heaters need to be prolonged. And one way of getting a material reaching the temperature of 1500, as I mentioned before, is to use a plasma. There are not many ways that can reach those temperatures, but a plasma can do that. And a plasma is something that you have a cathode and you have an anode, and between them you put some currency, and then you get this electrical arc, and you have to have a carrier gas through the plasma. And when the carrier gas is pushed through the electrical arc, then it gets the gas will reach a plasma state, and it will become very, very hot, up to maybe 5,000 Kelvin. Here we have chosen, as the question was asked before, of course, to use carbon dioxide as a carrier gas, since the main thing we would like to achieve is that with the concentration of the flue gases, with a CO2 concentration that is close to 100.
Hello, Bodil. Just
yes.
hopping in, we have less than 10 minutes on the presentation. It's still fine, but continue. But
yes, I think
to keep the timing.
Yeah, thank you. I'll try to do that. So what is happening if we look at a conventional rotary kiln for cement? You see here you did the temperature along the kiln, the radius temperature, and also along the kiln. You can see that the high temperature area from a conventional burner is quite long. It's along maybe half the kiln. But changing this heat technology to a plasma burner with CO2, it will happen. It will look like this on a theoretical calculation. You see that the temperature is higher, but it's very, very concentrated. It will be quite a small plume. So with this in mind, we were a bit anxious that we would not been able to get the high temperature of the plasma plume to the material. But theoretical tests show that if we tilt the plasma and if we add particles, then this will be changed, because in a conventional fuel burner, you have all the particles, which will give quite a high radiation. But in a plasma with CO2, it's only a hot gas, there is no particles, so the radiation is quite low. So with this in mind, we have been working in this Electra project, which is an EU-funded project, and we are trying to get this plasma heating in a rotary kiln for cement production on up to a TRL level of 7. And this is just a short description of the project. We are many participants, you can see here throughout the map, from Sweden, Norway, Finland, down all the way through Germany, Switzerland, Italy, Greece, Cyprus, etc. But the main thing here is high temperature and flexible concepts for the cement, lime, and pulp industries. It's Heidelberg Materials, it's Loast for the lime, and its pulp producers are Stora Enso. And our main thing here is that we will first done a lot of testing on a smaller, lesser TRL level, and then come up to this TRL level of 7. So I'll try to hurry up to get through them. It is a 4-year project. We are in the 2nd year now, and I'll show you here plasma and cement. So these are the electrical or the experimental kiln that we have been used for our test. It's a 300 kilowatt plasma we have used. You can see the plasma here. So the plasma needs gas, it's here, and it needs also to be cooled. So quite a lot of energy is removed, unfortunately. And then we heat the material, and the material is fed here. So it's a continuous countercurrent process. So it's an industrial-like in that way. We fed the material, the kiln, with approximately 80 kilograms per hour. We achieved a 70% CO2 atmosphere, which is a bit lower than we wanted. We want, of course, to increase more than 95, because that will be the best options for the gas cleaning, the next steps. But here you also see the product when it come out from the kiln, and here it's shown in a bucket. We did, during the test, advanced characterization, of course, of the heat transfer along the kiln, inside the kiln, and the kiln lining. We measured heat flux and intensity and temperatures, of course, and we also measured the flue gas composition and put a lot of effort in characterizing the material, of course. And what did we find? Well, we find interesting results. Here in the middle, you can see a typical cement clinker from a reference. The reference raw material here is not changed due to in common cement plant you get 1% of the raw material from the fuel ash, and we did not compensate for that in this. This is a traditional. Here is material run in the kiln 0. So here there is heat. It's heated with CO2, but still not corrected for the fuel ash not being here. We got very nice large nodules, black color, and plenty of coating and some boulder formation. So that was kind of sticky or problematic. But then we could optimize the raw meal, still based on the Skövde raw meal, and then we also optimize it for a CO2 atmosphere, and got a much nicer nodules, black color, minimal coating, and no boulder formation.
And
I think I have 8 minutes left.
Yeah, but it's still okay. But if you want to show the video, you can use the pointer and play the videos. Maybe with not the laser pointer, but the click. I've tried it and it works. So, yeah. So I've watched the video and it's.
Thank you.
You can understand better.
Yeah, see the small amount of material falling out of the kiln. Yeah. And this is for the optimized raw material. And we tested, as I said, 3 types of industrial materials, all based on calcium carbonate, because that is the common denomination for all the projects. Thank you. I'll continue with the next slide. So, as a summary, what did we find in this TRL5 kiln? So evaluation is still ongoing. There's many things to look into, but we got many interesting results and a lot of experience for the next step, which will be in TRL7 scale. And the heat transfer exceeded the predicted modeling results, which were very, very nice. And we got a high compressive strength of the product, higher than we thought, which is very interesting and usually what our customer wants to have. So for the next step, we are going further to increase the process scale, of course, and power. We need to improve the gas tightness. We had a quite old experimental kiln, and now we will start from the beginning and do it much better. We, of course, will continue and evaluate both the flue gas composition and, of course, the clinker quality, how it will be in the next kiln, which will look like this on a schematically. So it's much bigger. we are aiming maybe for a 10-meter long kiln. We will have an effect of 1 megawatt, so it's 3 times more than we have today. Of course, still continuous mood and approximately 400 kilograms per hour of raw material will be run through it. We need to improve the gas tightness. This is one of the main things. And here we have just some sketches on how we will decrease the gas leakage with some kind of piston, adjustable, close to the rotary kiln, and we have some other possibilities to tilt the plasma and add particles to the plasma to make the radiation even better. And this will be done next year, up and running and doing all the tests. And just a bit more about the Electra project. We're not only evaluating cement and plasma, we are evaluating many more demonstrators and also developing a new high enthalpy heated plasma together with Sintef and resistively heated rotary kiln at VTT in Finland. And we will test fluidized beds, both circularizing and bubbling fluidized bed heated with plasma and heated with electrical resistive heating elements. Those will only go for the partly electrification, as I also was talking about. And that was my presentation. Thank you for me.
Thank you very much. Thank you very much, Bodil, for the presentation. And we have several questions in the Q&A. So maybe the first, just a basic question. Maybe a misunderstanding, but now you are not using limestone to produce kiln. I mean, with the new plasma burner, is that right?
Yes, of course we are using limestone. Still,
okay,
yes,
so
that's a misunderstanding.
That's a misunderstanding. Yeah.
Yes, there isn't any material available in those vast amounts than limestone. So that is, that is still used.
Thank you for the clarification.
Yeah.
And a question about waste heat recovery with plasma. What can you tell us? Can we still do heat recovery with plasma? My expectation is not, but
I think the thing is we need to cool the material quickly to get the correct quality, and it's difficult to cool the material with CO2 or maybe to get it very gas tight. But if we can do that, we can take the CO2, then it's a bit warmer, and we can use it as pre-warm the raw material. This is something we haven't done here. This is not an energy optimizing project. It's more to see that we get the product, quality of the product and quality of the flue gases should be good. There are many options. Yes.
Okay. Thank you. Thank you for the clarification. Another question is about a question. Do you think plasma would be able to reach large scale, such as 4,000 tons per day? First question.
Yeah, I think that's one of the main issues. Today there are 10 megawatt plasmas available. As I showed you, we might need more than 100, 150 for a conventional plant. But I think also that thinking that just one plasma might not be the best option, because I think we can use parallel plasmas. But so I think the process, the electrified cement process will not look as today's conventional. So we will have a possibility to use several plasma, but they need to be, it would be, if they could increase to 50 megawatt, that would be very nice, for example. Yeah.
Okay. And also the same question was linked to the scale economies, like how it will compare in the future, but it's a tricky question how to answer. But with the conventional kiln of today, will it be more expensive? Can you tell something about this now?
Well, it's of course it's difficult to say, but when we have done on quite non-mature figures doing the calculations, we found that I mean we should not compare today's plant. You should compare today's plant with CCS, with the plasma. And if we use a plasma, we can decrease the gas cleaning drastically. Yeah, so I think that's the only question I can give, because I don't know what it will cost. But there are quite a lot of possibilities with electrification.
Thank you. And we have one last question about the carbon capture. You mentioned the total energy demand of about 5.5 gigajoule per ton of clinker in case amine-based carbon capture is implemented. Do you expect an energy demand decrease for the carbon capture part in the future? But so that's with the conventional one, and if so, by how much?
I'm afraid I think they are working. I mean, today we are using the amine solution, and they're working on it every day. So of course it will decrease, and how much? Well, we'll see.
Well, thank you for all the answers to the Bodil, very clear, and thank you for the presentation. Don't hesitate to ask other questions in the chat if they rise up. And I will invite now Andy Reynolds from FIV for the last presentation, but not least. And you can take the control. I will just share again. Sorry about that.
I think I have control.
Okay, but let me just, because the presentation was okay, and now you can take again the control. Sorry, we were a little lost. You can take back the control.
Okay, thank you very much, Leo. Thank you to the IETS for inviting me to give this presentation. I'd like to talk a little bit today about a project that FIVES did for a glass manufacturer.
Just a comment, Andy. You need to take the control again. I still have it. Perfect. Thank you.
Now I need presenting mode, which is.
It's all good for us, at least. We see the first slide of FIV.
Okay. So good afternoon, everybody. Yes, I'm going to talk today about a project that FIVES did for a glass manufacturer, Veralia Group. This project involves the electrification of glass manufacture. In terms of technology, the technology here is not new. What is new and innovative is the scale of the technology. It's a project where we were sort of upscaling existing know-how. So just a few words about FIVES Group. We're an industrial, multinational industrial group with headquarters in Paris. I won't go into all the detail here. Enough to say that FIVES is quite a diverse group. Our activities really can be divided into three main areas. That's high precision machinery, process technologies, including steel and glass manufacturing equipment. We don't actually manufacture glass or steel. And smart automation solutions like automated handling systems and this type of thing. You can see below some of the customers that we work for. If you need more information on the group, you can visit our site, fivesgroup.com. So glass production. Annually, approximately 120 million tons of glass are produced each year globally. That falls into four main categories. That's packaging, which is the largest type of glass. Flat glass is a close second, and then fiberglass, a little bit less, and then specialty glasses, including tableware, pharmaceutical, special electronic glass, that type of thing. Glass manufacture is a very energy-intensive industry. Especially the melting process. It's necessary to melt raw materials at very high temperatures. We're talking here in the order of between 1350 and 1500 degrees, depending on what sort of glass we're talking about. We do recycle glass into the process. We call it cullet. And furnaces can use anything between very low levels of cullet, 5%, 10%, up to very high levels of cullet. In terms of bottle production, it can be as high as 70, 80% cullet. But it doesn't really change the fundamental process in that we're using gas really to heat the materials. The dominant technology used today is what we call end-fired regenerative furnaces. You can see here in the picture the melting tank on the right-hand side, and then behind it are these large heat recovery structures. We use an air-gas combustion system, and we preheat the air coming into the burners using these regenerators, as we call them, which are heated by the exhaust gases coming off the process. And you go through a 20-minute recycling system. So you sort of the regenerator is in two parts. You heat one side of it on one cycle and use the other cycle to preheat, and then vice versa on an exchange. The raw materials are fed into the side of the unit. You can see here the picture on the left-hand side showing inside the furnace. You can use electricity to boost. We sometimes put electrodes in the glass to boost. It doesn't make a big difference to the overall concept. This technology is now pretty mature. It's been optimized quite well. These furnaces are actually quite energy efficient. But today, the industrial drivers really are the need to reduce carbon emissions. There's a legislative and consumer demand for sustainability. Long-term fuel economics, in terms of the relative cost of gas, carbon taxes, electricity, etc. And also the wish for technical agility. These furnaces, today, the current technology, these furnaces last for between 15 plus years. Some of them 20 years. So when you're investing in new technology or rebuilding existing technology, you have to be thinking about the future and what's going to happen within the campaign life, as we call it, of the furnace. So Verallia, where this project was set, Verallia is the world's third largest producer of glass packaging. They made a very strong commitment to sustainability back in 21-22. They made a commitment to reduce their CO2 emissions, that's scope 1 and scope 2 emissions. That's both usage of emissions from site and emissions on the energy that they use. To reduce those emissions by 46% compared to 2019 by 2030. And also a commitment to move to 60% renewable electricity by 2025, which is actually this year. In 22, they formed a strategic partnership with Fives, because Fives is a recognized, one of the recognized leaders in electric melting technology. And the purpose of the project was to electrify the melting processes at their Verallia plant in Cognac. This is in the west of France, where they make spirits for cognac and other premium drinks. They had an existing furnace, we'll call it furnace F1. This was 320 tons per day regenerative furnace, the technology I just showed in the previous slide. And the plan was to replace that furnace with two all-electric furnaces of 160 tons per day. So just looking at the melting process, in an end-fired regenerative furnace, if we want 320 tons per day of materials coming out of the furnace, we have to put about 355 tons of material into the unit. That's even with a 50% cullet rate, that's a 50% recycling of glass. We also use carbonates in the raw materials, and those carbonates decompose and produce CO2. So 30 tons of that 355 tons will be lost as what we call process melting CO2. But then on top of that, of course, there's the CO2 produced by the combustion system. And we're looking here with a furnace operating at about 4.5 gigajoules per ton. It'll be about 70 tons of CO2 produced per day. So a total of 100 tons or 102 tons of CO2 produced per day from the unit, which equates to 25% of the mass output of the unit, which is significant. So all electric melting technology is a little bit different. Here we don't use combustive energy input. We melt the glass electrically by passing current through the glass. We have molybdenum electrodes immersed in the glass through the refractory containing tank, and we pass quite large currents through the melt, and we heat the melt with the Joule effect, resistive heating. The furnaces operate in a slightly different way. The melting processes occur vertically, and we put the raw materials onto the top surface of the melt. So we call these vertical melters. The raw materials go on the top, and the fully melted, refined product comes from the bottom of the unit in what we call the throat. These furnaces don't have any combustion. They don't have any heat recovery structures. So structurally, they're much smaller, and they're very energy efficient. Certainly in terms of energy per unit of glass produced. So if we could go to an all-electric system for the Cognac furnace, we could replace completely the combustive input. We can't do very much about the decomposition of carbonates. There is work today on changing the raw materials that are used in glass manufacture to tackle to reduce the emissions from the actual melting process, but that wasn't a subject of this project. But here, if we can eliminate completely the combustive input, we can reduce dramatically the CO2 emissions. Of course, in France in particular, this is helped by the fact that the scope 2 emissions are very low, because in France, the CO2 cost of each kilowatt hour of energy, electrical energy, is low. In fact, I think at the time of this project, we were calculating on about 27 grams of CO2 per kilowatt hour of power. That you compare that with sort of an average in Europe of about 250 to 300 grams per kilowatt hour. So you can see in France, it's particularly attractive. So I said earlier, we wanted to replace one big 320 ton per day unit with two 160 ton per day units. And there's a specification there of each unit. I won't go through the detail. We have what we call a nominal load, a maximum load, a minimum load, a range of cullet ratios that the unit can work at. The image on the right-hand side is actually not the furnace; it's the actual bottle manufacturing machine that sits basically below the furnace, making the bottles. But the obvious question is, why not a single 320 ton per day furnace? And really the point here is about the project objectives. We wanted the glass industry is quite conservative. Of course, if you're investing in something for a long term, you don't want risk. We wanted to try and mitigate the risks associated with upscaling the design, the engineering, and the process from what we already knew. And the step of 160 tons was considered a manageable step compared to moving straight to 320 tons. This is because our existing technology up to that point is based on smaller units. Electric melting, as I said, is not new. It's already quite widely applied in cosmetic, tableware, and the pharmaceutical industry in furnaces ranging up to about 50 square meters, 50 to 90 tons per day. When I say 50 square meters, I'm talking about the melt surface that it's the primary way of sort of sizing furnaces. For the Cognac project, we were working at similar melt rates to cosmetic glass because the quality levels were quite high, and those melt rates are something like just over 2 tons per square meter, 2 tons of glass produced per day per square meter of surface. To get to 320 tons per day would have required a furnace of about 150 square meters. So that's 3 times what our current technology was. Whereas half that, the 160 ton per day, meant a melt area of about 75 square meters, which is we thought a manageable step up from existing technology. One of the other points was important with the project is that because electric furnaces are already very energy efficient, we're on the part of the curve of specific consumption versus design load, where the curve has already become quite flat. So in fact, 160 ton per day furnace is predicted to run at about 900 kilowatt hours per ton of glass. That's about 3.2 gigajoules per ton. If you size the furnace even bigger, you don't get huge benefit in terms of size. One of the big drivers for gas-fired furnaces has always been bigger furnaces are better because they're more energy efficient. That becomes less true for electric melting. So again, the move to the choice to have 2 separate smaller tanks rather than one big one was part of the consideration. And in fact, 2 smaller furnaces also offered certain advantages in terms of rebuilding, scheduling of rebuilds, etc., which the client was particularly interested in. I won't go into this too much. There was one of the big key points about the project was in terms of the shape of the furnace and the concept of the actual tank design. Needless to say that all of our designs are analysed and investigated, and one of the primary tools we use for doing that is CFD, computer fluid dynamic modelling. We build quite complex models of these furnaces, and we're looking at the temperature profile that we build, the residence time of the melt inside the furnace, which is a key part in determining the quality of the glass coming out of the system. And in fact, we determined that we could move safely from the standard hexagonal design that's used on the smaller furnaces to a rectangular design without endangering the quality of the product. The rectangular design was also considered to be a good option because it's a better stepping stone to even bigger furnaces, which might be considered in the future. So very quickly, the time frame for the project. We signed the contract in 2022. We built the unit during 23, and in fact, the unit was commissioned in the early part of 24. I think first glass was in April. So the furnace has now been running for just over 1 year. That's a quick image inside the furnace. Perhaps to much of the audience here, it might not mean very much, but it's for somebody who knows electric melting, it's quite a dramatic picture to see such a large furnace. That's a picture behind the furnace showing the batch charging systems. The long door that you can see on the right-hand picture, that's about 12 meters long from one end to the other. And this, I think, is a video which we can play, which shows the melting surface of the furnace. And this door is completely open to the outside, so you can see there's no dust, there's no emissions. The CO2 that is coming off the melting process is actually extracted through an extraction system just above the door.
I believe I've heard the loud noise from the furnace, and I did not hear you were saying during the video was played.
I was just saying that the CO2 that is coming from the melting process there is actually extracted at the back of the unit, so there isn't CO2 coming out to the door. So as I just said previously, startup was in 2024. Today, this is now the largest all-electric furnace operating in the packaging industry. So it was considered to be a milestone project for both Veralia and for Fives. That's the actual data, a snapshot of the data on the energy consumption. So you can see that the up and down is simply that they do job changes. So the load on the furnace is continuously changing. The cullet content is changing. So you don't get a perfect straight line, but it's tending towards the 900 kilowatt hours per ton, which was predicted. So it's behaving exactly as we anticipated. As I say, the furnace today is the largest furnace in the packaging industry worldwide. But we're now actively engaged, including work with Veralia to look at the next step. The next step will be moving closer to the 320 ton per day furnace that would allow us to go directly from one end-fired regenerative furnace to a single electric melter. Thank you for listening.
Thank you very much for the presentation, Andy. I believe it was really clear and appreciated here. And we have one question in the Q&A section as of now. Andrew, is there a realistic outlook for increasing energy input density into the material so you can reach higher output per day without increasing the melting area?
It's a very, very good question. Yes. Melting glass is, and I guess it's similar to many other industries, is always a balance between how quickly you can do the process and how much you stress your manufacturing equipment. So the glass is contained in a refractory tank. That refractory material has a life. It corrodes slowly, and that's what determines the life of the furnace. The only way of increasing melt rate is to increase temperature. But if you increase temperature, you reduce life. So it's a balance. You can cool the refractory to increase the life. And in fact, furnaces are cooled from the outside. But then, of course, your energy consumption goes up. So it's a three-way balance. And we, excuse me, we try to give the customer, our clients, the tools to allow them to some extent to choose how they position themselves within that balance. That there are cooling systems which can be applied to different levels, and yes, if they want to push the output from the furnace up, they can increase temperature, but the cost is a reduced life.
Thank you for the question. We've had a bunch of questions now. So quickly, can you elaborate quickly on the burner technology you applied in the surface? Did you use resistive burners, plasma burners, or I believe it was resistive burners, but maybe I misunderstood.
In the standard incumbent technology, these are air gas burners. These are just using preheated air with gas. Very nozzle mix type burners. In the all electric furnace, there's no burners. It's all done by resistive heating.
Thank you for the clarification. A question about the two new furnaces, about the spaces required. Do they claim more spaces than the conventional furnace? And was this an issue in the project?
It's another very good question. A lot of customers, prospective customers, the new technologies that are coming in, and there's electric melting, and there's other technologies that are being offered. Very often they have to fit existing footprints of within existing factories. And in fact, in the Veralia project, the new furnace fitted quite well within the existing footprint, because although parts of the furnace were like the batch charging system required more space, of course you don't have those big regenerators that you saw in one of the images. You don't have some of the combustion equipment that you need. So although sometimes the orientation of the furnace has to be slightly different, the space requirements are normally compatible with incumbent systems. So you can bring in an electric furnace into a factory where they had gas-fired technology.
Okay, perfect. And that answers the whole question so that was Christian from the Danish Energy Agency. I can see the title. Then next questions, is the electric furnace only suitable for container and specialty glass, or can it be employed for flat glass production?
Another very good question. It's one of those questions that the industry is tackling at the moment. One of the issues with float glass is the scale. I mean, a typical container furnace, a very typical container furnace, is 320, maybe 400 tons per day. A typical float furnace can be 900 tons a day. It's significantly bigger, and in fact, the regenerative technology is a little bit different. And as of today, certainly from Fives and from other similar companies, there's no technology for all electric melting at that scale to do it float. There are options, what we call hybrid, and in fact, that's the other avenue that most companies like Fives are exploring, where instead of completely eliminating combustion, you simply supplement the combustion with a very high level of electrical input. We call those hybrid furnaces, and those furnaces work on the horizontal melting principle rather than the vertical melting principle, and those are now being discussed for float furnaces. So as is today the case in the glass industry, there's not one technology for all different types of glass. There are sort of a number of different technologies, and I think that will always be the case in the future. So electric melting is not a global solution for all glass production. It can be applied to a lot of types of glass production, but perhaps not all of them.
Okay. And there are 3 questions left. I'm not sure we'll have time for those. We'll have to wrap it up. Maybe I can select how often, and you can reach out to Andy Reynolds afterwards, since you have the email here. How often is MO heating system to be replaced? So I don't know why I don't get the...
If MO is referring to the molybdenum electrodes, I think it could be. Perhaps that's the reference. The electrodes within the furnace are advanceable, so you can slowly advance the electrodes into the furnace, and the electrodes will therefore last as long as the furnace lasts. And they go through a water-cooled, we call them a holder, electrode holder. There's a water-cooled jacket to prevent glass leakage around the electrodes. But no, the electrodes have the same life as the furnace. The limiting factor for these furnaces of all types, electric and conventional, is the refractory containment tank and the gradual corrosion of the refractories.
Okay, thank you, and I believe you got it right. I did not, but I believe it was right. We have further questions, but I don't know, since some of you may have some other meetings following up. Maybe we can briefly wrap it up and ask via email your questions to Andy. I'm really sorry we cannot address them all. Thank you again, Andy. Thank you to all the presenters. And we'll have, I forgot to add it in the slide here, but we have, yes, thank you, Eileen Perhauke. We'll have another industrial series planned on excess heat recovery, probably in autumn. and Eileen maybe can complete. And I just wanted also to highlight the fact that at ALICE we are structured about industry decarbonization, and we'll have our third congress in September in Paris. So don't hesitate to check it out. And it's basically showcasing the mature, more TRL 8 or 9 projects to impact the industry. It's after R&D. And Eileen, maybe you can add a conclusion word, or did I miss anything? And you're
No.
muted. Okay.
No, I am so happy that so many people were listening to our first webinar in this series. We hope that there will be the same interest for the next ones. We haven't set the date for the excess heat one, but we will do that soon. And if you subscribe to our newsletter, you will get the invitation. First of all, thank you, everyone.
Thank you, everyone. And also the video will be uploaded on the IETS webinar in the next month, I assume. Thank you. I'm sorry, the cameras are it's just that we are so many participants, so it's less friendly atmosphere, but the interest was there. Thank you everyone for your questions, and I invite you to ask them directly to the speakers. Maybe next time we'll plan more time for the Q&A. But
yep.
Thank you all, and
and thank you, Leo. Good job.
Thank you. Have a good rest of the day, everyone. Goodbye. Maybe you can take further question. No, it was just.